Basically, what occurred before the enormous bang, right? You must be cautious with the language. So, assuming you characterize the huge bang very carefully as when the universe was extremely hot and very thick, furthermore, as I said, you can't argue with that since we can see it. We can watch out high. Our best hypothesis of how the universe got into that state is that there was a period before that, and it's called expansion. What existed before the enormous detonation? This question has always been a challenge for researchers, but now it seems they've found the answer. Anyway, it has left researchers stunned, as Brian Cox revealed that something frightening existed before the huge explosion. So, the idea is that the universe was in a sense cold and empty, and it expanded incredibly fast. That expansion slowed down and stopped, and the energy that was driving that expansion got unloaded into space, warmed it up, and made all the particles out of which we were made. That is what we call the enormous detonation. So, what existed before the huge explosion? Why has it left researchers frightened? Let's figure that out. That hypothesis has a sort of an extension called eternal expansion, which suggests that expansion essentially continues forever and only stops in small patches. Imagine this. The texture of the universe, space extends, stretches, and then it slows down and stops in small patches. Each one of those patches is essentially a big bang, and a vast expanse of which ours is one. You end up with an image of a boundless fractal universe, fundamentally an endless number of big bangs. That is known as the inflationary multiverse in the huge universe. The possibility of absolute nothingness seems hypothetical rather than real. Even if all energy were taken out from the universe, it wouldn't be really empty. At present, the universe is filled with matter, radiation, antimatter, neutrinos, dark matter, and dark energy. Even without energy, the universe still makes new types of energy. This phenomenon can confuse us. It seems the universe doesn't understand our concept of complete vacancy. If we removed all energy, leaving a void, one might expect the universe to reach absolute zero with no particles. Yes, that's not true. Indeed, even in an empty universe, its expansion would still produce radiation. This stretches far into the future, or even back to the time before the hot Big Bang. The universe, it seems, never truly becomes empty. Given this, is it possible that the universe started from nothing? We can be sure that something always persists, even if particles, antiparticles, photons, and quanta are taken out. Void space remains. If we move away from any mass or energy sources, clear the space of external electric, magnetic, and gravitational fields, and prevent photons or gravitational waves from entering, a sort of physical vacancy actually exists in space. Quantum fields persist, and the key constants and laws of physics persist. There is an inherent limited positive and non-zero value of zero-point energy in that space. This addresses the closest approximation to nothing within our universe. While you could imagine a much different state, it requires actual reality. No test can replicate such a condition by sticking to logical standards. We recognize that something always exists since genuine nothingness might not exist in our universe. But the question of why remains unanswered by science. By and large, our universe seems far from nothingness. It's interacting with stars, gas, dust, galaxies, quasars, cosmic rays, and radiation from both starlight and the remnants of the Big Bang. With improved observational instruments, we might be able to detect extra signals that we expect are present. This includes gravitational waves produced by any mass traveling through a changing gravitational field, puzzling signals from the constituents of dark matter, and a broader view of black holes, both active and dormant. Besides those transmitting the most radiation, everything we observe happens in a universe that isn't static but is constantly transforming. From a physical perspective, it's interesting to appreciate the evolution of our universe on a grand scale. The texture of our universe, known as space-time, is expanding. This suggests that if you place 2 points far apart in your space-time, the proper distance between those 2 points, the time it takes for light to travel between them, and the frequency of the light going from one point to the other, all increase over time. The universe isn't just getting bigger, it's also getting colder. As it expands, light stretches to longer wavelengths, moving towards lower energies and cooler temperatures. The universe was hotter in the past and will become even colder in the future. During this process, objects with mass or energy in the universe attract one another, forming groups and creating a massive, huge network. If you were to somehow remove all matter or radiation, each piece of energy, what would remain? Essentially, you'd have empty space itself, still expanding, governed by the laws of physics, but affected by quantum fields that fill the universe. This is the closest physical approximation to genuine nothingness, but it still adheres to specific physical laws. To a physicist, eliminating everything else would create an unreasonable state that no longer mirrors the universe we possess. This implies that dark energy, as we currently understand it, would still be present in this hypothetical universe without any trace of matter. Essentially, if every quantum field in the universe were set to its lowest energy state, we would reach the zero-point energy of space, where no extra energy could be removed for mechanical work. In a universe containing dark energy, a cosmological constant, or the z-point energy of quantum fields, it's possible that the zero-point energy wouldn't be truly zero. As the universe continues to expand and cool, there will come a time in the distant future when radiation becomes the dominant force, outperforming other forms of matter and radiation, leaving dark energy as the primary influence. However, there was also a time in the universe's history, not in the future, but in the distant past, when something else other than matter and radiation held power. During infinite expansion, before the hot Big Bang, our universe went through incredibly fast and steady growth. Rather than being dominated by matter and radiation, the universe was influenced by the field energy of expansion, much like the present dark energy, but far more powerful and expanding at a much faster rate. If eternal expansion is correct, but time is still limited, where could the universe have begun? There must have been a start, right? To fully address this question, let's disentangle three often conflated ideas and discuss each separately. The hot Big Bang in relation to our universe, the theory of cosmic or cosmological expansion and its role in continuing and preparing for the Big Bang, and the issue of an ultimate beginning or origin for our universe, and why both expansion and the original concept of the Big Bang may not provide a satisfactory answer to this inquiry. In the early 20th century, a significant union occurred when four key pieces of information came together. A breakthrough by Alexander Friedman in Einstein's general relativity showed that a universe filled uniformly with any type of matter and energy cannot remain static, but must either expand or contract, receding from us, further supporting the idea that the universe is expanding. This discovery by Hubble was pivotal, as it confirmed that galaxies are moving away from us in all directions, and the farther away they are, the faster they are receding. This observation became the foundation for the idea of an expanding universe, which is central to our current understanding of cosmology. Hubble's findings, combined with the work of Friedman and others, led to the development of the Big Bang theory. This theory posits that the universe began from an incredibly dense and hot state approximately 13.8 billion years ago and has been expanding ever since. The evidence for the Big Bang theory is not limited to the redshift of galaxies. It also includes the cosmic microwave background, CMB, radiation, which is the faint afterglow of the Big Bang, detected as a uniform radiation across the entire sky. The CMB is crucial because it provides a snapshot of the universe when it was just 380,000 years old, revealing a hot and dense early universe that was much smaller and more uniform than what we observe today. This radiation has been cooling over time, and its detection by the COBE, Cosmic Background Explorer, satellite in the 1990s provided further support for the Big Bang model. However, while the Big Bang theory explains the origin and evolution of the universe from a hot, dense state to its current form, it does not fully answer the question of what happened before the Big Bang, or what could have caused it. The concept of time itself, as we understand it, is intricately tied to the fabric of space-time, which was formed during the Big Bang. Therefore, asking what happened before the Big Bang is, in a sense, asking about something that may be beyond our current understanding of time and space. This is where ideas like eternal inflation and the multiverse come into play. As mentioned earlier, the theory of eternal inflation suggests that the universe's expansion continues forever, with regions of space expanding and stopping at different times. Some of these regions may even undergo their own Big Bangs, leading to the formation of separate universes, each with its own laws of physics. This idea leads to the concept of the multiverse, where our universe is just one of many, each potentially having different properties, dimensions, and forms of existence. Despite these fascinating ideas, the question of what came before the Big Bang, or whether the universe had a beginning at all, remains unresolved. Some physicists argue that the universe may have undergone a cyclic process, where it expands and contracts over infinite timescales. Others suggest that the Big Bang was simply a transition point from an earlier state, possibly involving quantum mechanics or other unknown processes. In any case, the search for answers to these profound questions continues. Modern cosmology, with its advanced observational techniques and theoretical models, is pushing the boundaries of our understanding of the universe. We may never fully answer the question of what happened before the Big Bang, but our growing knowledge of the universe's origins and evolution will continue to shape our view of the cosmos for generations to come. As we look to the future, the mystery of the universe's beginning remains one of the most compelling and awe-inspiring aspects of modern science, inviting both scientists and the public to ponder the nature of existence, time, and the very fabric of reality. Past our own, these discoveries, joined with different information, prompted the idea of the universe extending. Assuming that the universe grows, it proposes that over time, space itself extends, causing the matter inside it to become less dense. As space extends, radiation, like light waves, not only becomes less concentrated, but also stretches, prompting the universe to cool. If we rewind the clock, the opposite would happen. Matter and radiation in the universe, in earlier times when the universe was younger, were denser and hotter. If we rewind further, all matter and radiation would have been confined to a smaller space, increasing the density of the universe. The light, which stretched due to enormous expansion, would, when time is reversed, have had a shorter wavelength, resulting in hotter temperatures. If you imagine returning as far as physics allows, you'd reach a singular state where all matter and radiation existed within a single point of infinite density and temperature. The initial concept of the Big Bang theory resulted in the formation of 5 key assumptions about the early universe's hot and dense conditions. These conjectures became the foundation of the theory of how things came to be. The universe should exhibit expansion, as demonstrated by a specific redshift distance relationship among extragalactic objects. Initially, the universe must have been relatively uniform, with structures like stars, galaxies, and galaxy clusters gradually forming and evolving over time. In the past, the universe was hotter, preventing the formation of stable neutral atoms. This expectation led to the discovery of the cosmic microwave background, which is observable today. In the universe's initial stages, when it was very hot, atomic nuclei couldn't form stably. This led to the creation of light elements such as hydrogen, helium, lithium, and their isotopes. The universe was so hot that neutrinos played a critical role. Recently, this prediction was confirmed, showing that cosmic neutrinos should have noticeable effects on both the large-scale structure and the extra radiation from the Big Bang. With strong observational evidence supporting these predictions, our current understanding aligns with the Big Bang theory. However, in recent years, physicists have increasingly recognized the importance of the theory of inflation. It describes an even earlier, hotter universe while addressing some of the puzzles about cosmic structure formation, dark energy, and more. To recap, the concept of what happened before the Big Bang relies on our evolving theories of cosmology. What occurred prior to the Big Bang might be tied to eternal inflation or may involve fields and energies we have yet to fully comprehend. As we continue to explore these theories, we face the challenging question of whether the universe had an absolute beginning or is part of a broader, more complex structure that includes multiple universes or dimensions. The inflationary model, particularly the theory of eternal inflation, suggests that what we think of as the Big Bang is just one of countless local Big Bangs in an ever-expanding multiverse. In this view, our universe is essentially one bubble in a vast cosmic foam, each bubble representing a specific universe with its own laws of physics. Some of these universes could be very similar to our own, while others could have completely different fundamental constants or even different spatial dimensions. This multiverse concept challenges our understanding of the universe's origins and raises profound philosophical questions about the nature of reality, the beginning of everything, and the possibility of other forms of life or intelligence beyond our observable universe. Additionally, the more we learn about the universe, the clearer it becomes that the laws of physics as we know them might not apply in the same way when we look at the early universe or at tiny scales where quantum mechanics dominates. At these scales, quantum fields and particles are governed by probabilities rather than deterministic laws, and strange phenomena like quantum fluctuations become significant. These fluctuations could have been the seeds of the vast structures we see today, from galaxies to galaxy clusters, despite existing in what we think of as an empty state. As we push the boundaries of our knowledge with increasingly powerful telescopes, particle accelerators, and theoretical models, we find that the line between nothing and something becomes increasingly blurred. Could the universe have emerged from a quantum fluctuation in a vacuum state? Could our perception of reality be vastly different from what we understand? The further back in time we try to go, the less certain our answers become. What we consider to be before the Big Bang may be beyond the reach of current science. It's also possible that the universe in some form is cyclical. Some models, such as the ekpyrotic model, suggest that the Big Bang may have been the result of a collision between two branes, higher-dimensional objects in string theory, in a higher-dimensional space. This theory offers the possibility of an oscillating universe, where Big Bangs and Big Crunches occur in an eternal cycle with no definitive beginning or end. This adds another layer of complexity to our search for a definitive origin. The more we delve into the nature of time itself, the more speculative our ideas become. Time, according to some theories, may not have had a beginning at all. In a universe governed by quantum mechanics and relativity, time could be a relative phenomenon shaped by the presence of mass and energy. In this case, asking what happened before the Big Bang might not even be a meaningful question, as time itself might not have existed in the same way we experience it today. As we continue refining our theories, new data and discoveries will inevitably shape our understanding of the universe's origin and ultimate fate. Perhaps one day, we'll have a clearer answer to the question of what, if anything, preceded the Big Bang. Until then, we are left with profound mysteries, some of which may never be fully understood, but will continue to challenge our imagination and expand the frontiers of science. Ultimately, the pursuit of these answers represents one of humanity's greatest intellectual endeavors. Each new discovery brings us closer to understanding not just the origins of the universe, but the very nature of reality itself and our place within it. We may never fully grasp the origins of everything, but the journey to understand it will continue to inspire generations of scientists, philosophers, and thinkers to ask deeper questions and push the boundaries of human knowledge. As technology advances and our understanding of the universe evolves, the possibility of uncovering new aspects of the universe, like the nature of dark energy, the true origin of the cosmic microwave background radiation, or the potential existence of parallel universes, remains tantalizing. One day, we may find that the answers to these questions lie in dimensions or realms of existence we have not yet discovered, or in the fundamental laws of nature that are still waiting to be unveiled. In the end, whether we find a definitive answer or not, our quest for understanding will continue to shape how we perceive ourselves, our universe, and the mysteries that lie beyond. As humanity continues to explore the cosmos and refine its understanding of physics, the implications of our discoveries are bound to extend far beyond just the scientific realm. They touch upon philosophical, ethical, and even existential questions that have intrigued humanity for centuries. For instance, if the multiverse theory proves accurate, it raises profound questions about our uniqueness and the role of chance in the formation of our universe. Why does our particular universe support life? And could there be other universes where life, as we understand it, is impossible, or where entirely different forms of life exist? Additionally, the more we uncover about the universe's earliest moments, the more we grapple with the nature of causality itself. In our everyday experience, causes precede effects, but at the quantum level, this intuitive understanding begins to break down. This has led to radical theories about time, such as the possibility that time is emergent rather than fundamental, a byproduct of more basic, timeless principles governing reality. The pursuit of these questions also has practical implications. Advances in understanding dark energy, dark matter, and the fundamental forces of nature could revolutionize technology in ways we cannot yet imagine. Just as quantum mechanics and relativity paved the way for innovations like semiconductors, GPS, and nuclear energy, new discoveries about the universe's fabric could usher in a new era of scientific and technological breakthroughs. Furthermore, this quest for knowledge encourages collaboration on a global scale. Projects like the James Webb Space Telescope, the Large Hadron Collider, and other international scientific endeavors highlight how humanity can unite in the pursuit of understanding. These collaborations not only deepen our comprehension of the cosmos, but also serve as a testament to the power of shared curiosity and cooperation. Ultimately, the mysteries of the universe remind us of the limits of our knowledge and the boundless potential of our imagination. Whether we are peering into the depths of space, probing the smallest particles, or contemplating the nature of existence itself, our journey to understand the universe is as much about the questions we ask as the answers we find. As Carl Sagan once said, "We are a way for the cosmos to know itself." Our pursuit of the unknown is a reflection of our deep-seated desire to connect with something greater than ourselves, a reminder that in the vast expanse of the universe, we are both infinitesimally small and profoundly significant. In the years and decades to come, as new discoveries unfold, they will undoubtedly inspire not only awe but also humility. The universe, in all its complexity, is a vast, unfolding story, one we are privileged to be a part of and to strive to understand.